Hello student, welcome to our second lesson. Now here we are going to look at Boyles Law, but now we do some numerical examples. We start with the first one. A bubble of air of volume 1.2 cubic centimeter is released at the bottom of water dam 15 meters deep. The temperature of water is 20 degrees Celsius. Determine the volume of the bubble as it emerges on the water surface where the pressure is the normal atmospheric pressure. That is, take density of water as 1000 kg per meter cubed and the normal atmospheric pressure as 1.0 times 10 to the power 5 pascals. Now we proceed as follows. First of all, we always write the formula. Remember, P1 V1 is equals to P2 V2. But now how do we get the P1? Remember, this bubble is inside the water and that water is 15 meters deep. So to get now the pressure that is acting on that bubble, one, there will be atmospheric pressure, and then number two, there will be the pressure due to the water column that is above that bubble. Therefore, the total pressure will be the atmospheric pressure, which is 1.0 times 10 to the power 5 pascals, then plus the pressure due to the column, which is 1000, that is density times 10 times height. When you multiply this and then you add, you get that the total pressure P1 will be 2.5 times 10 to the power 5 pascals. Then pressure P2. Remember, now the bubble has emerged on the surface of the water, and therefore there is no column of water above it. Therefore, pressure P2 will be just the atmospheric pressure. Then V1 is given as 1.2 cubic centimeter. We are looking for the V2. Now for us to get V2, we can make V2 the subject of the formula from this formula. And we do that by dividing through by P2. So our V2 will be P1 V1 over P2. After getting the formula, then we substitute our values. Our P1 is this value, 2.5 times 10 to the power 5. Our V1 is 1.2 cubic centimeter, and then our P2 is 1.0 times 10 to the power 5 pascals. When you key in these values in your calculators, you find that the value of V2 will be 3.0 cubic centimeters. Then number two, a narrow uniform glass tube contains air enclosed by a 10 centimeter thread of mercury. When the tube is held vertical, the air column is 600 millimeters long. When tilted slightly, the air column is 679 millimeters long. The temperature is the same in both cases. That is, the temperature is constant. So part one, give the reason for the differences in length of the air column for the two positions. Remember, now we are saying one, it is vertical, the other one, it is lying or horizontal. Now, when it is vertical, the mercury exerts pressure on the air. And when we have that increased pressure, there is a reduction in the volume as per Boyles Law. Then part two of the same question, you are supposed to determine the atmospheric pressure at that place. We are also given the density of mercury as 13.6 grams per cubic centimeters. Now, this is our case. When it is vertical, we have 600 millimeters of air column. When it lies horizontal, this volume increases to 679 millimeters. So in our first case, we have said that the reason for the differences in volume is because in our first case, this column is exerting pressure. And when there is increase in pressure here, there is reduction in volume. But now when we want to get the atmospheric pressure, first of all, we have P1 V1 is equals to P2 V2. But how do we get the value of P1? Our P1 is here. It will be the atmospheric pressure and also pressure due to this column of mercury. So our total pressure will be P atmospheric plus now the pressure due to this column, which is given by the density times G times height. Our height was 10 centimeter, so by converting it into meters, you get 0.1 meters. And when you multiply, you get it will be P atmospheric plus 13,600 pascals. So this will be the total pressure P1 on our first case. Now our P2, because this one is lying horizontally, now the weight of this one is acting downward, so it is not exerting pressure on the air that is trapped here. Therefore, the pressure P2, it will be just atmospheric pressure. Now, for us now to work, we need to get the cross-sectional area, and we are letting that area to be A, so that now we can be able to get the volume. So our volume V1 will be the cross-sectional area multiplied by the height. So you get 0.6 A cubic meter. Then our V2 will be 0.679 A cubic meter. From there, we have our formula P1 V1 is equals to P2 multiplied by V2. Now we substitute our values. We have our pressure P1 as this one, our V1 as this one, then pressure P2 as our atmospheric pressure, and our V2 as this one. Now because A is common, we can cancel out A. Then from there we open the brackets. It will be 0.6 times atmospheric pressure. You get 0.6 multiplied by P. Then this one multiplied by this, that is 0.6 times that is 600. You get that it is 8,160. Then we have 0.679 multiplied by P. You get that as the value. After that, we need to bring the like terms together. And by so doing, you get that this side you are left with 8,160. Then when you take this term on this other side, it will be 0.679 minus 0.6 atmospheres. From there, when you subtract, this will give you 0.079. And this side you have 8,160. Now to get the atmospheric pressure, you divide through by 0.079. And by so doing, you get that your atmospheric pressure will be 1.0329 times 10 to the power 5 pascals. Then we move to the other example. Air is trapped inside a glass tube by a thread of mercury to 40 millimeters long. Now, when the tube is held horizontally, the length of the air column is 200 meters or millimeters as shown here. We have that it is lying horizontally, we have the atmospheric pressure, we have the volume here, and we have the thread of mercury. Now, given that the atmospheric pressure is 760 millimeters hydrogram and the temperature is kept constant, calculate the length of air column when the tube is 1 held vertical with the open end up. Now, in this case, remember when it is like this, we have the pressure due to atmosphere, that is the atmospheric pressure, and we also have the pressure due to the column of the thread of mercury. So the total pressure will be the atmospheric pressure plus the pressure due to this. So the total will be the 760 millimeter hydrogelum plus 240. You get that it is 1000 millimeters hydrogelum. That will be our pressure P2. Now P1 V1 is equals to P2 V2. So you get P1 as 760 millimeter hydrogelum, then multiplied by V1, which is 200, and this will give you 1000, which is our P2, multiplied by V2, which is our L. That is the length. Now for you to get length, you divide through by 1000, and you get that your L will be 152 millimeters. Then number 2, you get the column when the tube is vertical with open end down. That is, it is inverted as shown here. Now, if you look at this diagram, you will find that there is atmospheric pressure. Remember, atmospheric pressure acts in all directions. And that is why in our case here we have the upward. And now we have this part or this thread of mercury that was here. It is acting downward. So now we need to get the resultant pressure. And for us to get the resultant pressure, you subtract, that is 760 minus 240. You get now that the pressure that is acting here will be 520 millimeters hydrogelum. Now from there we have our formula. P1, V1 is equals to P2 multiplied by V2. So we substitute our values. We have 760 multiplied by 200 is equals to 520 multiplied by L. So our L will be 760 times 200 divided by 520. And you get that your L is 292.3 millimeters. Then after that, we have the assignment. The assignment here is testing what we have just learned. So make sure that you practice a lot, you discuss with your peers, and then come and attempt the assignment. So thank you and enjoy.